So good afternoon, everyone. Welcome to today's wireless distinguished seminar. So before I introduce our speaker, for those of you who are attending this webinar for the first time, so please feel free to leave your questions in the Q&A section at the bottom of this window at any time during the talk. And we try to actually answer all the questions at the end, but if there are some pressing questions, we'll like that during the talk as well for our guests so with that, I would like to start. It's our great pleasure and honor to actually have Professor Daniel Bliss to our distinguished seminar today. Professor Bliss is a professor in the School of Electrical, Computer, and Energy Engineering at Arizona State University, and the director of ASU Center for Wireless Information Systems and Computational Architectures, WISCA. Dr. Bliss received his PhD and master's in physics from University of California, San Diego, UCSD, in 1997 and 1995, and his bachelor's in electrical engineering from ASU. His doctoral work was in the area of high energy particle physics and lattice gauge theory calculations. Before moving to ASU, Dr. Bliss was a senior member of technical staff at MIT Lincoln Lab for a number of years, till 2012. And between his undergraduate and graduate degrees, he actually worked for General Dynamics on a few high-profile engineering projects as well. So he's an accomplished engineer, such as the Atlas Center launch vehicle and high-energy particle accelerators. His current research, though, focuses on advanced systems in the areas of communications, radar, precision positioning, advanced computational systems, and medical monitoring. His research is funded by multiple organizations such as DARPA, ONR, Google, Airbus, and others. And he has done some foundational work on electrical protection, adaptive MIMO communications, MIMO radar, distributed coherent systems, and RF controls. Dr. Bliss is also a member of IEEE AES Radar Systems panel and a member of IEEE Signal Processing Magazine editorial board, and also a fellow of the IEEE. So with that, Professor Bliss, I would like to thank you and welcome you for being our distinguished speaker today. And without further ado, the floor is yours.
Well, hello, everyone. Thank you very much for having me. I recognize these are under strange circumstances, but on the upside, I can make breakfast or make lunch for my daughter, give the talk, and then go back and make dinner too. So in some ways, I guess this makes life a little bit easier. All right, so I'll start off by talking about some just introductory stuff about ASU, my center, and for amusement's sake, I'll repeat some of the things about my background just because I think it's kind of amusing. And then I'll do a quick overview on a number of projects that we have, sort of a slide each, just to give you some sense of breadth of the sorts of things that we're thinking about. And then I'll really focus on the processor that we were developing for DARPA and spend most of the time on that. All right, so ASU. So Arizona State University is a rather large university, depending on how one defines the size of a university. We're the largest university in the US or not, since there are various ways to define it. We've been around for a while, but frankly, even though we were a reasonably large university, we were a little sleepy in terms of research until maybe a couple decades ago, and then there was a decision made that ASU should become more serious about research, and you can see over the last couple of decades that our research expenditures have grown rather dramatically, and we're clearly heading heading towards $1 billion in sponsored research, which is a remarkable number. So we were the largest engineering school in the US. We have an awful lot of students. And we have a reasonably large electrical engineering program. We call ourselves electrical computer and engineering, energy engineering. We have, well, last time I counted, these numbers move around on me a little bit, 78 faculty in the School of Electrical Computer and Energy Engineering. The computer engineering program is technically over in, we'll call it computer science, even though they have a different name for it. So if you were to include those, we would even be larger, maybe well past 100. There are a fair number of electrical faculty in electrical engineering that do computer engineering. It's just that the formal computer engineering school is over in computer science. All right, and as you can see here, we have lots of buildings. So Ashu actually mentioned that his background was the picture of the original building at Rice. So now I feel obligated to point out to Old Main down here in the lower right, which was built right around the start of the university, around just after 1885, and it's still there. I'm pretty sure it's been gutted many, many times and rebuilt on the inside, but it's still there. All right, and once again, this is just for amusement. So I did my undergrad at Arizona State long ago. And while I was there, I worked for Motorola, Motorola Government Electronic Systems. So while I was undergrad, about half time I worked at Motorola. When I graduated, I went to San Diego and worked for General Dynamics, and there I worked at Rocket Avionics. So I worked on the thrust vector control of the upper stage of the Atlas Centaur, which at some point was just called the Atlas. And then I started working on superconducting magnets for particle accelerators. This was still at General Dynamics. It may seem strange that General Dynamics would work on large superconducting magnets, but it turns out the people you need to do to work on the upper stage of the Atlas Centaur rocket, you need those people for cryogenics, and it turns out so General Dynamics got very good at cryogenics, and it started working on superconducting magnets as well. Anyway, then I went back to UC San Diego, got my master's and PhD in physics. But even though I was a UC San Diego graduate student, and it would make a lot of sense to stay in San Diego since it's one of the most beautiful places on the planet, I almost immediately went to Cornell, did all my research at Cornell while I was a UC San Diego student. So decisions, I guess. Then when I graduated, I went to MIT Lincoln Laboratory and spent 15 years at MIT Lincoln Lab, learned a ton and had worked on lots of fun projects there. And then looking around, I came back to ASU. Now, people often assume that I came back to ASU because I started at ASU. It's just about the opposite is true. I mean, I enjoyed my time at ASU as an undergrad, but my view of it was kind of as a sleepy, more instructionally focused university, and not so focused on research, and research is what I cared about. At some point, I ran across some article about ASU, and I found out that the ASU that I had in my head had nothing to do with the ASU that was existing now. So I had to rethink my biases, I guess. All right, so WISCA, that's the Center for Wireless Information Systems and Computational Architectures. That's the center that I run. And we really want to go from basically concept theory to actual implementation. I suppose that this is influenced by my time at MIT Lincoln, where we would go from theory to actually building stuff. I still have this instinct where I want to go from theory to actually building stuff. I really do think it's important. If you don't have an experimental system, it is very tempting to go try to solve problems which are maybe not the most important part of the problem set. And when you actually have to build something and get it to work, you quickly recognize what the key problems are. Anyway, so we want to enable a next generation of wireless systems. We got tons and tons of commercial software-defined radios I've lost count now, but we must be heading towards 50 EDIS radios in my lab at this point. We have some really cool tools for actually operating those radios as a network, but I won't go into that today. And we have some other toys as well. We build our own custom SDRs or semi-custom SDRs as well, and we do all sorts of experiments indoors and outdoors. And what you see is my former students, now research scientists, doing there is flying an octocopter where we have one of our SDRs, and we were doing some propagation experiments. So doing fun stuff there. And then we get to actually developing high performance processors, which I'll spend a bunch of time on, so I'll skip that for the moment. And we ended up working with lots of interesting funding sources and companies. So more money comes from DARPA than any place else in my research, but I've done a lot with Google and Viasat and Airbus. And then I've worked with a fair number of companies as well, as part of teams, say working for DARPA as an example. All right, so let's start thinking about the sort of some technical background. Probably because of where I just sort of landed at MIT Lincoln, I spent a lot of time thinking about adaptive processing across multiple antennas. And so all sort of like the fundamental tool for processing, in my point of view, is space-time adaptive processing. That is, I can take multiple antennas, I can incorporate various delays, and I can mitigate undesirable interference to my comm system. Or actually, a similar processing chain is also used for radar as well. And so if there's some interference, whether this is intentional or unintentional, or even if this is a multi-user system, we can use these tools for going after all the users in the environment. So that's one piece of it. That's the spatial processing. Even though there are time taps in this, we'll call this spatial processing. There's also temporal processing. And so if I have an estimate of what's actually sent, then I can project onto a temporal basis, which is orthogonal to that signal. And actually, because our environments often have some delay spread, what I really do is not just project onto a basis which is orthogonal, but I project onto a basis which includes some delay structure as well. This is also important if you're not exactly time-aligned as well. And so by doing this, I can remove interference. And then, in general, you actually mix these techniques. So we've known how to do this for a very long time. The problem is these calculations are expensive. And so we need to figure out how to perform these operations and make it not expensive. All right, so this is our fundamental toolkit of how we actually disentangle multiple signals that we want to look at simultaneously. All right, so now this kind of moves me immediately to this next set of problems. So we'd like to provide a better way of actually using our limited spectrum. So the idea is that we reuse the same RF signals and receivers to perform multiple functions simultaneously. That is, we can co-design our systems so that the same RF energy is actually performing multiple functions, comms, radar, other sorts of sensing types of problems or applications. Receivers can receive multiple signals simultaneously, and because we have the tools to disentangle multiple signals, we should be able to actually deal with that. So because we have access to these tools, right, we can build systems where the processing is all joint, and potentially by having access to multiple paths to the environment, we can actually improve rather than degrade the performance. So we're not just trying to mitigate annoyances, but we can actually use the information from multiple sources to get better performance. This is particularly interesting maybe with a multi-static radar system that's simultaneously a comm system and a multi-static radar system as an example. All right, and all this stuff is basically enabled by recent technical advances. That is, we can have flexible RF front ends, and we can have efficient computational systems. And as I pointed out before, I'll talk about how we're trying to push that much further. So examples, well, there are certainly DoD applications where it's useful to have multiple capabilities with the same RF front end. Interestingly, if you think about what's happening in the automotive industry right now, particularly as we're moving towards more semi-autonomous and potentially fully autonomous systems, it's probably going to be that you can't even buy a car pretty soon that doesn't have a radar system or actually a suite of radars on it. And there's a standard for actually the vehicles to talk to each other, although that hasn't been used very much. That's a whole separate system. And then there's another system which is related to GPS, which is just its positioning system. So, if two cars want to talk to each other, maybe they receive their positioning information from GPS, they have a comm system, and maybe they talk to each other. They have a separate radar system that actually looks in front of it. And, the same car that you would like to get relative position, navigation, and timing, you would like to know its position based on radar, and you would like to be able to talk to it, let it tell you what it thinks is going on. Separate stovepipe system, even though they're all trying to go to the same place. And so this doesn't make any sense at all, right? We could reuse the same RF energy to provide multiple functions simultaneously. So we should think about doing that. And then you go to the very small case. So, millimeter wave is coming to a phone near you, apparently. So that millimeter wave front end, it's intended to allow you to have a high data rate. So why not use that same front end to actually, maybe measure gestures or something like that from your phone and use it as a radar? And that may sound silly, but actually Google built a system to just do that specifically. They built a small scale 60 gigahertz radar that's about the size of a postage stamp. And they're using that for basically gesture control. So you can actually measure the hand position. Now you might ask, why would you do that? Well, one reason is that your phone might be in your pocket and you just want to be able to control it, some sort of human machine interface, control it, without having to pull it out of your pocket, because let's face it, we're all pretty lazy. There's a second reason though, which is if you think about the way we normally interact with a phone, it's swiping your finger across it, right? So we spend half our lives in moving your finger around. It turns out we did not evolve to be very good at that particular motion. So that's a sort of a low information content motion. But we are very good at very tiny micro movements of our fingers, right? This is what we're really good at. So if we can take advantage of the fact that we're very good at that, there's a lot of information that's contained by tiny, tiny motions of your fingers. And if you can estimate that, then you can use that as a human machine interface. Well, there are lots of other things which I'll talk to about as well that's interesting about these small scale radars, but it's an interesting opportunity once you realize that I no longer have to think about these systems as single function systems. Potentially we can learn all sorts of interesting things about our environment by using these front ends to do multiple functions simultaneously. All right, so I actually threw this slide in at the last moment because this came up in multiple conversations today. So you can imagine that I have multiple subsystems that have multiple needs. That is, I'm trying to communicate, I'm trying to estimate something about the environment as I'm trying to get a radar return. And I would also maybe using that same sort of what traditionally we would have called a radar, I can use that maybe as a base station too. So I'm going to simultaneously receive signals, send out signals, and try to and also see what's going on in the environment. So there are at least 3 different metrics. And in fact, if you think about it for a while, you realize there are more metrics of performance, but we'll just focus on a few of them. And so we can think about the rate, the data rate of the comms. We can think about the data rate of the relay coming back out. And then we have a metric which we call the estimation rate, which is sort of how much are you learning, how fast are you learning something about a radar target. And we can theoretically define the performance of these various parameters. In this very simple case, because we can do this, and because this is a very simple space, we can then say, well, I would like to optimize some weighted combination of the performance, right? And then if you go ahead and do that, you can get this surface, this optimization surface. And then you can move around this optimization surface by saying, oh, the relay comms performance is more important, or the radar is more important. And you can move around the surface and find the optimal set of parameters. Now, That's already moderately complicated, and maybe this is the wrong combined metric anyway, but at least it's simple to write down. If instead of having just sort of 3 nodes, imagine I have dozens and dozens of nodes, all of which have maybe more complicated set of needs and weird sets of resources. That network problem, that network optimization problem, is a very rich problem. And I've talked to multiple people today about that's probably going to remain a rich problem for quite a while. Understanding even how to write down the problem is complicated. Then going through the process of solving it, once you realize that these nodes, which have to make decisions, have stale information about what's going on with other nodes. And so you have to make decisions, you have to optimize the joint system resource management while, you know, trying to satisfy your goals and not adversely affect someone else's goals all at the same time. It's a rich problem that's going to stick around for a while. So anyway, just wanted to put that out there. So another problem that we're working on is distributed coherence, distributed beamforming. In order to do distributed beamforming, you need to be able to basically maintain the coherence between a set of nodes. So here I have a bunch of, say, CubeSats as an example, but this can be on the ground as well. If I have n nodes, it turns out, and I cohere them up and beamform to something, then what I can get is an n squared power scaling. I'm getting to that node. So that's nice. But the problem is I have to basically be able to phase all these items up, you know, to within a small fraction of the wavelength. And that's tricky. So we've been working on techniques to actually enable this, and this is related to some of our extremely precise positioning, navigation, and timing work. And so what we can do is we can actually determine the relative position of one node with respect to another node to within a small fraction of a wavelength. So we can actually do that positioning. And we do this through timing exchange. So that basically our one node communicates to the other node, it estimates the time, it sends back. So this is basically the network timing protocol that your computer uses, except that this is an incredibly precise version of this that allows us to actually pull out something which is really small. So if I had lots of bandwidth, if someone gave me access to lots of bandwidth, this is actually not that hard. We can go after these sorts of problems. In this particular case, we're assuming that we do not have access to a lot of bandwidth because, let's face it, bandwidth doesn't come cheap for these problems. And so we're trying to basically position something given very, very small resources. So in particular, we were allocated 10 megahertz of bandwidth around gigahertz. And given that, we needed to estimate the position to something small compared to 10 centimeters because there are FAA requirements that are related to that. So using these techniques, the timing exchange techniques, we can very, very quickly do ranging estimates to not just less than 10 centimeters, but actually something small compared to 10 centimeters. And here you see something where we're getting closer to millimeter-like accuracy. And you know, for a gigahertz signal, it's a tiny fraction of a wavelength in terms of arranging. I won't go into details on this. It was great fun. We actually built a system, real-time system that works. It has other features that's fairly robust. So for you know, Airbus, who funded this work, their interest was in producing a alternative PNT approach to make flying cars safe, or urban air mobility, as they call it. So as I said, we took something where the intrinsic ranging resolution was about 30 meters because it's 10 megahertz bandwidth, and got something down that's sub-centimeter. All right, and so another topic that we've been thinking about is conformal arrays. So if you imagine if I wanted to just drape an array over some surface, whatever that is, there are lots of interesting problems associated with doing that. And so we actually went down the path of going, well, what can we do if it's a fully digital array? So people get excited about fully digital arrays with you know, hundreds of, you know, over 100 individual elements. We decided to go much further along this path. Like, we're thinking about fully digital arrays with tens of thousands of elements. And so now it's a huge problem. And it turns out actually you quickly hit a transition point where your real problem is actually trying to get data through what would have used to been called an antenna. Now it's really a data network. How do you get this data through there, and how do you do that efficiently? And there are lots of techniques that we've used to study this. This is still at the study level. We haven't actually built this, but we've done portions of this. And one of the things we came up with is statistical modulation. So basically, each antenna element, it's effectively a one bit A to D or D to A, and so we can use that information and use it probabilistically to, really build arbitrary constellations, even though any individual element only has access to one bit real, one bit imaginary, or off. We can also, at the same time, use these techniques to do the tapering across the array. And as I said before, a big problem is actually the data, moving the data around. And so we've designed these hierarchical approaches. It's basically a hierarchical data network to minimize the amount of data that actually has to be moved across this network, because that ends up being the dominant source of power consumption. Anyway, so that's a lot of fun, and it's kind of fun to think about problems where you go to huge numbers of elements as opposed to just 100, as it were. And then we've been thinking about small scale cardiac radars for a long time, actually small scale radars in general. In fact, we've launched a company now, the Big Little Sensor Company. We've gotten pretty good at. We have multiple techniques for actually extracting heart rate and breathing, and working on some other things as well. And so we're up and going with that. So that's a lot of fun. The whole problem area is interesting too, I think, in the small scale radars, because when they get down to the point where they're basically the size of a postage stamp, I think there are all sorts of fun things that we can start pulling out of these devices. All right, so finally to the actual topic. Let's think for a second about system design trees. And it used to be that we would go on trips, but clearly this is an example where we're not. At some point we'll probably return to this. And if you go on a trip, often you end up renting a car. And when you come back to the car return, rental car return, it's this sort of weird environment where there's this long column of cars and somebody waves you in to one of the columns and you go up and pull up. And then they come out and somebody with some sort of tablet or iPad asks you a question or two, and they check on the status of the car. That's it. So if you think about this, there's only a few thousand bits that needs to be transferred, right? But it is a kind of a rich environment because it's like a big metal structure and it's steel and metal reflectors all over the place. So it's very echoey. And then if you look around, you'll notice that there's a Wi-Fi router sitting there, almost always. And then if you look a little bit longer, you notice there's another Wi-Fi router, and you keep looking around and recognize the whole place is just seeded with Wi-Fi routers everywhere. And it's an interesting problem because Wi-Fi is built in everything, so you're tempted to use it. But in fact, it's a bad standard for this problem. It's completely overwhelmed. Wi-Fi is completely overwhelmed by the multipath in this environment. And it's really designed for high data rate. And what we have is low data rate, but we want it in a rich multipath environment. And we'd like to basically, cover the whole thing. So we get stuck using the wrong standard, and it ends up being sort of a mess as a consequence. So we really need a better waveform and protocol. But, you get sort of stuck because the SOCs, you need customized SOCs to make these things efficient. And building a full custom SoC is expensive. And, we did some estimates on this. To actually get to the point where you get a full standard with a family of, companies that are supporting the SoC, it's billions of dollars per standard. So clearly you're not going to have lots of these. And then, as well as I do, we only have a handful that we try to solve all our problems with just a handful of these standards. But all these choices are based on decisions we made because we assume that only those standards are available because only those standards are supported by the SoCs, by these custom SoCs. So you have these rigid computational capabilities, that limits your engineering options, that reinforces the limits of engineering options, and you get stuck in the cycle, right? And people don't even realize they're stuck in the cycle because they've been stuck in the cycle so long, they can't even imagine that it could be different. All right, so what we're gonna try to do is actually break that. So we're building a processor that's flexible and efficient. All right, so we can do this by saying we're going to focus on a particular domain. In our case, we're thinking about RF problems, primarily communication systems, but it can also do some radar processing and some PNT sort of processing. Can you see the kind of problems that I want to address? It certainly has influenced the sort of things that are going to be on this chip. All right, so we would like to have the efficiency of a full custom chip. So we want that sort of efficiency, that sort of teraops per watt. But also we want to be able to do this without the staff costs of building a full custom chip, which can be hundreds of staff years. So the alternative is a scalar processor, like the one that's in your laptop, which is wonderfully flexible and relatively easy to program, although anyone who's programmed anything large will probably argue with me, but relatively speaking, easy to program. But it is actually comparatively rather inefficient to the full custom chip. All right, so I'm going to just ask for things and say we're gonna move to this point where it's both easy to program and it has the performance that approaches that of a full custom. We're going to do this by building a heterogeneous processor, so I'll talk about that. And not just the processor itself, but actually a whole framework to support that. I'll explain why as we go along. We really want to make sure that non-experts can do this. And by doing this, we can break that sort of rigid computational capabilities problem, and I can get my flying car. All right. So let's think about this for a second and compare our options maybe more quantitatively. So, there are lots of different kinds of processing solutions, right? And the standard solution is something for like LTE. If you go LTE sort of flat out, it's about 300 milliwatts on a custom IC. It's really low power. It is a thing of magic. But let's say you want to do something else. Well, good luck. You got to redesign the whole chip. If you want to update it afterwards, it's not happening. If you want to do multiple simultaneous applications on the same thing, it's just not going to happen. It's just not going to happen. Your staff will quit. All right, so you go, okay, got it. I'm going to go to a fully flexible system by going with scalar processors. Certainly, there are good examples of people who have done this, but it's a fair amount of power, right? A flat out high performance processor to try to get the system going. It can be 150 watts, and depending on what you're doing, it might not even be able to make the throughput required. All right, so if you got a rack mount, you have a system that's full of rack mount computers, you can get this to work, but you don't want that in your pocket. So next step is the FPGA. DoD has invested heavily in using FPGAs for software-defined radios. Try to put that on there, and it's expensive. Order 30 watts to get that working. I heard some estimates that it'd actually be higher. Maybe you can get it lower in some cut down version. But anyway, to get that working, it's probably at least 15 staff years to get that up and going on the FPGA. You want to do a post-deployment update, certainly possible. And it's probably another 5 staff years. And if you're trying to do multiple simultaneous applications, it's probably not going to fit in the FPGA to put it in the system. Certainly, that's always been a problem when I worked on FPGA systems, is that as soon as you start doing anything interesting, you're out of fabric. And you probably give up. All right, so you're like, all right, heterogeneous processor. Heterogeneous processor basically means that I have a bunch of accelerators that are good at various things. LTE, it's not going to be as efficient as a full custom processor, but if you do it right, you can get pretty close. So we're going to say maybe it's 600 milliwatts. If you try to do some other kind of quirky waveform, Well, if it's really quirky and it didn't match the accelerators you put on there, you're lost. You're gonna try to do a full new waveform with new custom threading. So it turns out the threading through these heterogeneous processors is a nightmare. I'll come back to this and talk about it some more, but that ends up making you suffer. And I tried to do a post-deployment update. It really is a lot of work to get it working, because once again, you got to change all the threading through the processors. It's almost like starting from the ground up. You're gonna try to do multiple applications, trying to thread it through this sort of standard heterogeneous processor, what I'm calling a standard heterogeneous processor. You're gonna give up. All right, let's get this to Dash. So we have all the advantages of the standard heterogeneous processor, because that's what we are. If you try to give us a non-traditional waveform, we actually embedded in our processor, we have some accelerators we call DAPs, which are actually sort of these high performance systolic array processors. And so we're pretty flexible, even though we're focused on accelerators. So we have a nice sort of while we're accelerator driven, we have some nice flexibility as well. I'll talk about why I think we can actually do new things without a lot of staff. And then if there's a post-deployment update, it won't be that big a deal to actually update it. And we have a requirement from DARPA that we're going to be able to execute multiple simultaneous applications for under 5 watts. And I can tell you right now, we're in the middle of development. That seems perfectly reasonable. All right, so let's think a little bit about why we went down the heterogeneous processor solution. So if we have an overview, or whether we have an overview of sort of different classes of processors, and here is the GOPS or GOP per second per watt, and sort of as a surrogate for time, we have node technology along the horizontal axis. You think about a scalar processor, which we said was nice and flexible. Various forms of vector GPUs, FPGAs, and then the full custom ASICs, which are dramatically better than all the rest. So we want to go from basically a scalar processor to this, which gives us over a couple orders of magnitude in terms of performance. The reason why you think that might be useful, if you take a look at a typical application, and I'll just use a multiple antenna receiver example, you take a look at the sort of tasks you do and what's computationally expensive. There are typically a handful of tasks which completely drive all the computations. So it could be like in this case, the matrix multiply is the most expensive part, and the FFT is also expensive. QRs, back substitution, are expensive, and then the error correction is expensive. And depending on which kind of problem you're solving, the order of these might completely change, and maybe the FEC is more expensive than anything else. But it will be something where there are a handful of these types of operations which completely dominate the computations. And then you have a large number of higher layer tasks, all of which are relatively cheap. So we can dump all of these on a general processor and specialize for these. And that's the motivation for the heterogeneous processor we're developing. So we have an ARM cluster on it. For those who care about security stuff, we have red-black separation. We have a very nice high-performance network on chip. And then we have various accelerators in here for doing different sorts of applications, a couple different DAPs, which I mentioned on this thing. We have this kind of cool, flexible error correcting decoder, which is actually quite interesting. And a really important piece of this is the is here. The IS is the intelligence scheduler. So we'll talk about that a little bit as well. All right, so how do we make this all work? I have some C code. I want to get it going on the dash. So if you take a look at what happens, and this is just an example of a few different processors and T matrix multiply decoder for different applications. That's going along the horizontal axis here. If you take a look at how they use these different accelerators, you notice based on this the scheduling plot, it's all very different. And so traditionally what you do is, if you're really careful, you carefully hand thread how data is moving through the chip. Our problem is that we want to make it quick and easy to do this, right? And we want to actually have multiple applications running simultaneously. So the idea that you can hand thread to the chip doesn't make any sense at all, right? Because you don't even know what the problem is when you send it out, and it has to figure it out on the fly. And so we really do need to reduce the reliance upon the implementation expert in order to get the cost down. And I will tell you, I know of multiple examples where people built heterogeneous processors and then got only one application to run on it. This is a common thing to happen. It's effectively a full custom chip. All right. So, and we need to simplify the compiling, debugging, and scheduling. It's just, you need to make it easy so normal humans can actually program this in. So to do this, so we're studying the kinds of applications that we want to operate. So we actually have this huge repository of code for the kind of applications that we're interested in. We do an ontological analysis of that code, determine the computational relationships. That helps us with lots of things. It helps us with determining what the SOC floor plan should be. I mean, that's useful, although to be honest, any engineer that's been working in the area will probably figure out, how to do this, but still. But that gives us the design for the network on chip, the requirements of the network on chip, and also potentially gives us the hardware design. All right, so we learned about what we want from the ontological analysis. Right. Also, it provides the directed acyclic graphs associated with the processing that is happening in the code, and also we use it to identify what are the key kernels in that processing. And if you think about any particular task, so let's use the FFT because it's kind of fun. I can implement that FFT in the FFT accelerator. I could implement it in the ARM processor. I could implement it in either of the DAPs. Actually, there are multiple ARM processors. I could have implemented across one or the other ARM processors as well. And so we build these, what traditionally we call fat binaries. We're trying to find a better name than that, maybe chimeric binaries, but basically include implementing these tasks in multiple ways. So this is done automatically as well. Then we need to be able to do debugging. So we actually working with ARM to build a nice interface, which standardizes the interface between the various accelerators, and it makes debugging easier too, because this is one of the nightmares we've had before. We worked with previous generation heterogeneous processors. You send stuff into it, nonsense comes out, and there's no way to debug it. And if you have multiple ones, whatever information you're getting from one accelerator to another accelerator, the way you debug them is different. It's just a nightmare. So this way, we are developing a standard about how you actually interact with these accelerators, and this allows us to have a sort of a standard interface for debugging as well. Then we also use the information that we get here to help us with the intelligence scheduler. So we have multiple techniques that we are implementing for the intelligence scheduler. Currently, sort of the winning one is to use imitation learning. So offline, we use Oracle, which is computationally very expensive let me rephrase that. We use computationally expensive techniques to determine what good approaches are for resource management. We call that our Oracle, and then we do imitation learning to basically learn to act like that. That's our intelligence scheduler. And you get all this stuff together, and then you can actually produce an efficient real-time implementation. All right, so we have lots of accelerators that I already mentioned. The DAP is a lot of fun. So as I mentioned, it's sort of like a high performance systolic array processor. Won't go into details. Paper's coming out soon, so I won't spoil this. But we actually sent off a test chip on this. This is the part of our team is University of Michigan, and they're leading this, and I'm very excited about how this is going to turn out. Once again, this is really nice because this allows us to do lots of linear algebra, which is basically most of RF processing. It's very good at doing sort of linear algebra kind of problems, and so we have that. We also have the unified forward error correction accelerator, which I mentioned before. It is a relative of the DAP in some sense, and by using this, we can actually cover a reasonable fraction of error correction codes that are in use. And once again, it's also very efficient while remaining flexible. All right, so for the sake of time, I won't go into details, but we've been making lots of progress on this. Lots of things have been either demonstrated on FPGA demos, and like I said, we actually sent some stuff off. We have lots of aspects which have actually, the RTL for. And a part of the program is that we're developing actual radios with this chip. So it's dangerous just to build a chip because if it's not actually embedded in a real system, you'll probably fool yourself about what's going on. So a portion of the team, actually we have 2 team members, there are going to take the chip and actually use it to do radio functions. All right, so here's our path. We've sent out the first test chip. Right now we are working on finishing up the design for the first spin, going to Global Foundries. That will go out first couple months of next year, and then we'll have a more sophisticated second spin on chip. We're going to use those outputs to basically work in our software-defined radios that General Dynamics and Collins Aerospace are going to develop. And at some point, we hope to actually get to getting this up on a LEO satellite. I've actually talked to a number of potential users for small sats. This is a perfect chip for a lot of applications there, so we look forward to trying to get something going on that as well. All right, so we're having lots of fun. I've been wanting this chip for the last 20 years, basically, because this enables all the fun stuff that we like to do in a sort of sophisticated signal processing sense. We are very focused in the development of this chip on making it useful. And really, it's key, and I can't overemphasize this. We have to make it so you can actually program this chip. And so a lot of work, probably half the work, maybe more than half the work on the team, is actually in developing the software that supports the use of the chip. And we have some really cool accelerators developing for this as well, and working towards the actual demonstrations. So I'm the PI in Arizona State University's a prime, and really, I can't stress this enough either, have an absolutely wonderful team. So these are our team members you see listed here. Lots and lots of wonderful people working on this program, and it's very exciting to be part of this. So I'll say in closing, I want to once again thank all the people on my team who are working very hard to make this all work out. And that's it.
All right, perfect. Thanks a lot, Dan, for the great talk. So I guess we have a few questions. So the first question is from Ashu. So
I can just ask directly. Yeah. So Dan, again, fantastic talk. Very ambitious project. So good to get all the details. I guess could you comment on any thoughts on the fact that in wireless there is all these standards, or also have different spectrum bands they use? So any thoughts on making that part more programmable? Also on the radios and the amplifier side, so then the whole radio chain is a lot more flexible.
Right. You didn't ask one question. You asked about 20 there, whether you intended or not. So yeah, everything needs to become more flexible. So there are a fair number of programs, including programs at DARPA, to enable more flexible front ends. As you well know, one of the big issues, given the current way things are set up, is that you're basically you're forced in a situation where you have to use pre-selection filters. Otherwise, out-of-band interference tends to overwhelm you. There are techniques to go after fixing that. Polyphase mixers is one idea to go after these sorts of problems, to try to reduce the reliance upon those pre-selection filters. And then there are other people trying to basically make flexible pre-selection filters to improve that performance. So there's that level of problem, trying to figure out how to move more seamlessly through the frequency. There's a policy problem as well, which is we've been building things this way for so long. When you talk to somebody on the policy side about breaking all these rules and trying to come up with a new way of doing this, they just look at you like you have three heads. But that's true at the start of everything. So, I mean, I'm pretty sure the people who came up with the ISM band said, so long as you follow some basic rules, you can do whatever you want. I'm pretty sure that people went, you're nuts. You can't, that will never work. And yet that's been the most productive band probably in all of existence, is the ISM band. So much great stuff has come out of that. I think what we want to do is develop a next generation ISM band where we assume the individual nodes have capabilities which allow for moderately sophisticated, or require moderately sophisticated interference mitigation capabilities. And that way we can actually have a more interesting set of capabilities in that band, as opposed to the ISM band, which is, be nice, don't step on your neighbor's point of view. I think I only answered 3 of your.
No, thank you. That's good. Yeah, I will let others ask questions, but yeah, thank you.
Okay. The next question is from Joseph Cavalar. Joe, you want to go ahead?
Sure. Yes, thanks. Enjoyed your talk, Dan. Very interesting. Also, the idea of communications and radar using the same hardware. My question, though, is I have two. The first one is a philosophical question. What are your thoughts on ARM versus RISC-V, especially now that NVIDIA has acquired ARM? RISC-V is very flexible, and people are also designing a number of SOCs around the RISC-V instruction set.
Sure. All right. I'm trying to not get myself in too much trouble in answering this. RISC-V has been the solution that's going to happen 3 years from now for a long time. Eventually, it will be the solution. So at some point, RISC-V is going to be the solution, and I don't know how ARM is going to deal with that. But from my perspective, at the moment, the answer is ARM. There's just a lot of support for it, and it's easy for us to work with. From our perspective, we're sort of agnostic. If at some point RISC-V ends up being the winner for us, then we just swap out and put RISC-V on it. That works for us. We have no ties, but just from a system engineering point of view, right now, it's the ARM. It's very convenient for us to use it. And maybe that's an unsatisfying answer, but
no, it's okay. I mean, there's some aspects of the fact that it's open source hardware and some reasonably flexible compiler support that seem to be interesting. It's getting a lot of buzz these days, and there are some chips, especially from the groups there in Zurich and Bologna. Luca Bonini's group has been actually developing some designs.
Yeah, so I actually recently talked to some folks at Google who are very interested in trying to have a sort of an open structure for these things, and they're very interested in pushing RISC-V too. I think, like many open source problems, you at some point you hit a critical threshold of enough users using it that it suddenly gets good enough that then a lot more users use it. And once you hit that magical point, then all of a sudden everybody jumps on board. And I don't know exactly when that's going to happen. It's bound to happen at some point.
Okay, my second question, if you're ready, is how do you feel that Dash will compare with something like, let's say, NVIDIA's Xavier chips? They're more flexible. They're intended for more mobile applications. They have tensor cores that are kind of like the DAP. They have regular GPUs, they have ARM cores, and CUDA is not that bad. My students are able to program CUDA pretty effectively, even though it's multi-threading. So I'm just kind of curious, how do you feel they compare in a way?
Yeah, so our expectation is that ours is a bit tighter in terms of we will actually be better in terms of power performance for multiple reasons that I didn't go into details on. But I mean, you're not wrong that they're a competitor. It's just that we're very focused on a particular class of problems, which makes us be able to focus a little bit more clearly on those. Whereas they're really, well, they're trying to solve a similar set of problems, but they're still stuck with this kind of broader worldview, what they're trying to do with it. I don't know. I might be being unfair to them because I'm clearly tied to mine. But I do think the fact that we're very focused on a smaller set of problems allows us to be more efficient on those problems.
Okay, I think they're trying to push into the more base station ORAN kind of environment with their new aerial software-defined radio tools, which try to optimize for some more base station type applications, I guess.
Yeah.
Okay, thank you very much.
Okay, next question is from Ray Timar. Ray, would you like to ask the question?
Sure. Yeah, thanks a lot. First, Dan, I really enjoyed the talk. You're definitely going after a problem that is super important. And so I want to kind of get a feeling for how you saw some of the alternative solutions. And you had a really nice graph that was sort of talking about FPGA and GPU and vector. And so how do you kind of compare GPU versus vector? Sort of what's vector mean to you kind of in this case?
Yeah, well, first of all, I have to thank John Brunhaver for producing that plot. He did it much faster than I ever would have. The GPU processor, of course, is intended to do graphics sorts of things, right? The vector processors were sort of competing to it was more like the signal processing kind of vector processors. They're clearly cousins. So I'm.
Yeah, and I guess the GPUs have a lot of overhead, because you're not doing graphics, right? So they've got that problem. And then, so who would you consider an example of a vector machine today that you would point to?
So one that we were considering for a while is the IP that SIVA produced.
Oh, right. Yeah, sure.
And I think we almost went down that path.
Okay, yeah, I know what you're talking about there. Yeah, cool. So that'd be kind of, yeah, I see why you're kind of calling that a vector machine. I think, yeah, that's really good. I guess too, what about some of the VLIW kinds of stuff?
I don't know, give me an example, help me out.
Well, I know like Tensilica has some VLIW stuff that are like 4 wide, and they're finding a lot of use in some heavily compute, mobile, low power kinds of applications. And I don't know if you had looked at any of those. I mean,
so I personally have not actually spent much time thinking about this.
Okay.
So I'd have to defer to somebody who's thought about it some more.
Yeah. No, I mean, there's more than enough things to look at. That's for darn sure. But I really like the idea of how you're going to be able to kind of morph the solution okay, I don't necessarily have to do, matrix multiply just in one place. Maybe I could do it in another place, that kind of stuff. So I think it's really going to be interesting. It's going to be great to see it come together. Thanks a lot.
Yeah, it actually has been really interesting to have the application teams working with us, both Collins and General Dynamics, because they've actually forced us to think about problems that we had sort of ignored, because they gave us sort of sort of their favorite RF problems and things they absolutely need to solve. This is like real life. They need to solve these problems, and they have forced us to think a lot about the standard set of problems, getting data on and off, but certain aspects of that, and also how we which accelerators we need to put in there, what are the characteristics of the accelerators, and also how do we save energy or save power when things are in a lower power mode. Anyone who's worked with radio systems know that 99% of the time you're basically doing nothing, and so if it's sitting there burning power while you're doing nothing, then clearly that's the worst case scenario. So trying to minimize the power consumption and actually match the power consumption to the computational operations is key in all this. So one important thing that we're doing as an example is that we're very flexible on the clock rate on the network, which allows us to reduce power rather significantly when it's not important to move data around so quickly.
Okay, so like maybe in that case, will you almost sort of envision that you'll load in the software kind of and configure the system and then run for a while, that kind of thing?
Yeah, I mean, it's we expect the load to move around on us though.
Okay.
I think that's probably what you're really asking.
Yeah, right.
Yeah, so we don't expect a static environment. We don't expect a static set of tasks. We expect these tasks to be constantly dynamically changing.
Cool. All right. Thanks a lot.
Sure.
Okay, I guess we don't have any other questions from the audience, but I guess I want to ask the last question, which is actually along the same line of the previous question, which is actually, I guess, the goal of the DASH system is to actually design a flexible system at the same time for making it high performance. And that actually kind of made me think about the issues that we have in software-defined radios, where when we want to essentially design a real-time wireless system, what we have to deal with is essentially guaranteeing latency, which is actually one of the kind of important issues of any sort of standard. So I was wondering how the user of the system can actually guarantee latency.
Yeah, so that's a really interesting problem, and of course we're working on this because otherwise nothing works. But it's richer than you might realize, because different tasks that might be running all simultaneously have completely different latency requirements, right? So, LTE, I got a couple milliseconds to turn around the processing. But if I'm simultaneously doing SAR processing, it could be 10 seconds, right? I mean, to do a whole scene, and these things are operating at the same time. Maybe that's a bad example because they're so different that they don't actually compete necessarily for resources. You just always give it to LTE until it's done. But there are other ones where it's closer, right? If I'm doing a couple different comms waveforms simultaneously, they have similar ones and trying to compete. So so we're folding that into the intelligence scheduler. That is you have this sort of higher level task that the entire task needs to compete, and so we have different weights basically for these tasks so that we can make sure it gets done. Of course, given a system though where it's dynamic, there is no absolute guarantee, but with some high probability.
Okay, fantastic. Thank you so much. So that actually ends our today's distinguished talk. I would like to thank everyone for attending, and thank you, Dan, for the fantastic talk.
Thank you for your time and for the opportunity. I very much appreciate it.
Thanks, Dan.
Thank you.
Yeah, thanks.
Thank you. Thanks very much. Thanks, Dan.